So I assume you guys were all too busy celebrating Easter to do homework too. Is that accurate? Okay. Well,
I didn't know it was Easter until like 11 p.m.
in dynamics, I asked if anybody asked something about the homework, and like literally not one single person in class.
Oh, I was late. That's why.
Oh, okay.
I did it.
All right. So last time we started talking about the stresses due to shear force. And we can do it for two cross-sectional shapes. The first one is rectangular. And what needs to be bigger, the height or the width? And we talked about that, did an example. The only other one we can do is circular cross-sections. And we can only do it at the neutral axis. And really the only reason that's useful in the least is because the maximum stress due to shear force occurs at the neutral axis. So sometimes if that happens to be all that you want, then it can be useful. So the good news is that that's where the maximum stress due to shear force occurs. That's not saying that that's where the maximum stress occurs, though, because if there's also tension or compression or a bending moment, you know, the location on the cross-section where the maximum stress occurs and the maximum total shear stress, for example, there's no reason that it has to be there generally. But if you're only worried about the stress due to shear force, then that's where the maximum shear stress due to shear force occurs. Okay, so so here's what we need to talk about. And the calculation is still the same. The XY shear stress is still equal to negative VQ over IB. Q we can figure out because this is the area that we care about. And this is the distance in every case because we're never looking at any other locations. So Q is equal to I have it here. Oh, okay. So Q is equal to pi r squared over 2. That's the area. Times the distance from the midline to the centroid. And you can just look that up on a centroid formula. And that's equal to 4r over 3 pi. And so the pi's cancel. And you end up with 2/3 r to the third. So this is the only Q that we use for circular cross sections. And then the moment of inertia, the area moment of inertia, is equal to pi r to the 4th over 4. You can get that from a table. And that's the only one of those that we're going to use. So let's do an example. So let's say we have this cantilever beam. And let's say that the mass of this beam is 1,000 kilograms. It's 1 meter long. And the cross section is circular. With a radius of 0.2 meters. So what's the stress tensor at the neutral axis on the beam's midpoint? All right, so the first thing we have to do is calculate the external loads and then figure out the internal loads at the line of interest. So this is where we want to figure out those internal loads eventually. If you want to be smart about it, you could just right away do the cut from the right, but we're not trying to be smart, we're trying to be consistent, you know? Being smart isn't our style. So I'm going to just take the extra step of just calculating the external loads and doing that. Okay, so 9810 acting down. Then we have the reaction force and the couple, MR, and then the 20,000 Newton horizontal force. So Newton's second law says Rx, Ry plus 0, negative 9810 plus 20,000, 0 is equal to zeros. So R is equal to negative 20,000 and then positive 9810. And then the moment equation, I'll do it about the left. So we have MR. The moment armor of this 9810 is 0.5. Yep, and that's negative. And then there's no moment from the 20,000. So MR is equal to positive 4905. Okay, so now we'll do the cut right at the midpoint. So x equals 0.5. There's no reason we have to calculate the functions. We can just calculate it at the point we care about. There's a reaction force over here of negative 20,000, positive 9810. And then there's a reaction couple of 4905. Then there's the weight. So since we're looking at half of the beam, it's going to be half of the beam's weight acting right at the midpoint. So that's 4905. And then the internal loads, T, V, and M. And I'm going to leave off the torsion because there's nothing going on about the x-axis. It would just be 0. So Newton's second law says negative 20,000, positive 9810, plus 0, negative 4905, plus T negative V is equal to 0. So T is equal to 20,000. And V is equal to positive 4905. And then the moment equation, the moments are computed about the left, so 4905. And then what's the moment arm of this 4905? X over 2, and x is equal to 0.5. We're not doing a range here, so this is going to be 0.25 times 4905 and negative. And then plus m minus vx equals 0. So m is equal to vx plus, what's that? Quarter of, who knows? That's impossible. Oh, I've seen that number before. How did that work? 1,000. Oh, yeah. Okay. 1,226.25. And then minus 4905. And x, we know what x is, yeah. So that says something went wrong here. Something went wrong with the sign, I think. Minus, so plus, minus, that's going to be plus. Oh, this should be negative, this shear force. I just did the algebra wrong. Oh, you're right. Okay, well maybe this is right. So,
Why is it wrong? Why do you think it's wrong?
why did I think it was wrong? I just looked at it. I didn't see this 9810, so I thought I just said that V was equal to positive 4905 when it should be negative. But that's wrong. That 9810 is there. So that is right. So maybe all this is right. It's a little. Okay, so.
When you're doing this right now?
What?
Like why do you think it's supposed to be like
Because when you do it with x as a variable, at least, you always get like a cancellation between, a partial cancellation between the term that comes from the weight and the shear force. But let's just plug this in and see what we get. So m is equal to 24 52.5 plus 1226.25 minus 4905. So that is, what's that?
Negative 1226.
Okay. And the downside of doing this just at a single point like this, for that single x equals 0.5, is we can't do the derivative checks. You know, if we'd done it as functions, we could check the derivatives, and that would give us more confidence that we did it right. The good news is, whether this m is right or wrong, it's not going to affect our answer for this problem. Yep.
What if we're not gonna, like, let's say, gonna solve this problem without plugging in 0.5 first, and then checking the derivative, and then just plugging the number in
Yeah.
at the end?
Right. Yep.
Then we can actually check if we did the right thing.
Yes, that's right. Okay, so why won't this affect the answer? That's right, because we're calculating the stresses at the neutral axis, and the bending moment doesn't have any effect at the neutral axis. Okay, so now we can go on to calculating the stress, and the stress tensor is equal to the stress due to tension plus the stress due to the bending moment plus the stress due to the shear force plus the stress due to torsion that we haven't talked about yet. This is 0. This one's 0 because of the neutral axis. And so we just have to deal with these two, the tension and the shear force. So for tension, the XX stress is equal to the tension divided by the cross-sectional area. So positive 20,000 divided by the area is 0.125. And so you get a stress of 1.6 times 10 to the 5 pascals. This is pi r squared. Did I round it a lot?
I don't know.
Okay. And so the stress tensor due to tension is 1.6 times 10 to the 5th, zeros everywhere else. And now due to the shear force, Q is equal to 2/3 radius cubed. And in this case, that is 0.0053. I is equal to pi times the radius to the 4th over 4. And for that one, you get 1.257 times 10 to the minus 3rd meters to the 4th. Oh, this is another thing that's always the same. That B in the formula is just the width of the cross-section at that point. So this is just always equal to R. Let's add that up here. Yes. I thought that 2 was implied. Because it's a diameter. The width is a diameter, not a radius.
So you're just looking at the.
You're just looking at, so we're taking the stress along this line, and so you're just taking the width of the base at that point, which is the diameter. So 0.4. And so the XY shear stress is equal to negative shear force. So that's 4905. Times Q. Divided by I. Divided by B, and you get negative 5.2 times 10 to the 4th. So the stress tensor due to the shear force is 0, negative 5.2 times 10 to the 4, 0, negative 5.2 times 10 to the 4, 0, 0, 0, 0, 0.
So the units on B meters?
Yes. And so then the total stress tensor is the sum of those two that we calculated. So that's 1.6 times 10 to the 5, negative 5.2, negative 5.2 times 10 to the 4, 0, negative 5.2 times 10 to the 4, and then zeros everywhere else. Okay, so we figured out the stress tensor at any point along the neutral axis at the middle of the beam. Let's figure out now what the maximum shear stress is at that point. So what that question is asking is, somewhere there's a coordinate system where the shear stress is as big as possible for this same point that we're representing here. What's the shear stress for that coordinate system? It could be this one, but most likely it's not. Okay, so what do you have to do that? 2 steps.
Eigenvalues?
Yep, first you have to find the eigenvalues, and then you can just use that formula to find the maximum shear stress. So do that quickly. 1.75 times 10 to the 5th minus negative 1.54 times 10 to the 4th divided by 2. And what did you say, 9.52 times 10 to the 4th. Okay.
Why did we cross out the moment tensor again?
Because the stress due to the bending moment, that formula is negative m times y divided by I. And that y tells you how far you are from the neutral axis. So if you're at the neutral axis, y is equal to 0. And so you don't get any stress for that.
Oh, okay. So,
So yeah, so anytime we're looking at a circular cross-section, there's not going to be any question about, you're not going to have to calculate the bending moment, the stress due to the bending moment, because it's going to be 0 at the only place that we can calculate the shear stress.
It also works for solids and those hollow circular beams.
It also works for hollow circular beams, yeah.
I mean, would it be beneficial to, like, if you to only calculate along the neutral axis, and then you can, like, figure out other stuff from there, or what? I mean, the original question is at the neutral axis, right?
Right.
I don't know. I guess only if you're kind of only concerned about that spot.
Yeah, that's all you can do. Otherwise, I mean, there's a lot of reasons you'd be concerned about other spots, but we can't do that calculation. I don't. It's a little complicated, and I don't have that in my head. But if you're curious enough to come to my office, I can show you that. It's like all this stuff just depends on certain assumptions, and the assumption here, I believe, it's related to the fact that you're assuming that the shear stresses are vertical, and so like if you're higher up on a circular cross section, then they would be angled like tangent to the circular cross section, and so the assumption doesn't hold. And so we can only do it for the one spot on a circular cross section where the shear stresses are, vertical.
Can you do half of them? Like, since you're going up, can you do just one at a time, or it still doesn't work? Like if you consider your distance halfway instead of just the full distance. You know what I mean? Like if you consider the circular, your circular beam.
Yep.
And as you said, as you go up, your things become more like kind of tangent to the. So instead of dealing with both of them, can you just deal with one, or it always has to go up instead of going?
It always has to be up and down.
Okay.
Just because of the assumptions, and I don't remember what the assumptions are, but as you go through this sort of long derivation, one of the assumptions you make to be able to, in this derivation, is that you don't have any components of the shear stress that aren't straight up and down. But other than that, I don't remember the details.
You're not supposed to rotate at all.
Yeah, well, it doesn't do you any good in this case. Any other questions? Okay, so the next thing we have to talk about is stress due to torsion. And to understand what's happening here, imagine that you have this long torsion member. And think about, I'm going to draw it finite, but imagine this being infinitesimal. So this is, think of this as like a stress cube on the surface of this stress element. And what? Gaussian? Okay, so say that this thing is in torque like this. And imagine that this is like rubber or something, where the deformations are visible. If you put this member into this state of torsion, what's going to happen to that element? How is it going to deform? What's it going to look like after the deformation? Yeah, it's going to be twisted. And the way it's going to be twisted is like this.
Doesn't it also mean
Nope. All it does is angle change. It doesn't change length or anything, it just changes angle. Yep. And so now think about what kind of shear force you would need to make a stress element do this. On this side it's down, and then that means on this side it has to be up. This side it has to be that way and that way.
When twisted like that, right? It's not like coming out of the page.
No, right.
Oh, okay.
It just,
That makes more sense.
yeah.
It went this.
Like on this side, points are doing this. On this side, points are doing this. And so that's the deformation you get. And then if you just think about what it takes to make a stress element do this, you see that the stress is in the XY direction. Four points directly in the positive Z direction from the center line. Okay, so think about that for a second. So can you imagine what's happening on the back, to elements on the back or on the top? Yeah, so on the back, if you have one of these red elements on the back before deformation, after you twist it the same way, so you twist it like this, something on the back is going to be higher on this side and lower on this side. Okay? Something on the top is going to be farther towards us on the right side and farther into the page on the left side. But we'll deal with all that stuff with rotation matrices. So all we need to think about is if you have points that start out directly in the positive Z direction from the center line, like this point I drew here, a positive torque on it is going to make the right side drop down. Okay, so we'll do calculations of the shear stress the shear stress on circular cross sections and thin-walled closed cross sections. So these would be like, we'll be able to do stuff for tubes like this or this. It doesn't matter if it's circular or not. But if the tube is solid, then it has to be a circular cross-section. We can't do this. I don't remember why that is either. You can imagine that if you, I think intuitively it makes sense that if you applied a torque to a shape like this, and watched what deformations are happening, it's going to be much more complicated than in something where all the way around, remember the piece next to it is supporting this piece, you know. This is going to, like, one side's going to warp out, one side's going to warp in. It's going to be complicated. And I don't remember where that comes up in the derivation either, but.
Are we able to use what we're learning right now? Able to use this to actually construct something and calculate and construct something in real life that would actually work for us?
Yeah.
We still have to go into finite elements to do.
And I mean, as long as they're fairly simple shapes, or close enough to these simple shapes that you know you can get good approximations. And you know you can't figure out much near where the external loads are applied because of St. Venant's principle.
How would you even like the only way I can think of applying the right amount of like newtons that you want, like trying to model one of these,
Mm-hmm.
is like with weight and gravity. But how do you apply like newtons from the side? You know.
Yeah, you could do it with like a threaded, you know, some kind of like jack system or something. You could, I mean, if you're just trying to do it in the lab, MTS, you know, it's like a Twin Cities company, is like the main company in the world for designing testing machinery for that kind of thing. So they design, for all sorts of different applications, they design equipment for figuring out what loads something can take and applying very accurate loads here and there. But, you know, in Twin Cities Engineering, they do a lot of welding their own test rigs and figuring out ways to use load cells to apply forces and torques to things. And I don't know, it's pretty interesting. If you're curious, you should, I'm sure you guys all know some people over there. You should ask them for, I'm sure they'd always be happy to give you a little look at the kind of stuff that they've built to do exactly that. Yeah. Okay, so we have one mathematical preliminary we need. And that's called the polar moment of inertia. The integral definition looks like this. I sub p is equal to the integral over the entire cross-section of rho squared dA, where rho is the distance from the center line to the increment of area that you're looking for, so 2 dA. One thing to notice about this is that polar moment of inertia, it can be calculated for any cross-sectional shape, but we're only going to use it for circular shapes. We're going to use we're not going to use this in calculating those thin-walled shapes. So it can be calculated for any cross-section, but we'll only do circles. So let's derive it. So let's derive the formula for I sub p of a circular cross-section. Okay, so using any kind of integral definition, what's the key to getting through the derivation? What's the key step? The key thing you have to choose right in order to make this work. What? I would say, to me, that sort of falls into place usually. Really, the key thing is defining your increment, your infinitesimal, in this case, area dA. If you choose that in a thoughtful way, so that, and so then, to me, everything else falls into place. And that's just the way it is with all of these things with integral definitions. So here's how we're going to do it. So there's the circle, and our increment of area is going to be an infinitesimal strip where this distance is r. And actually, I'm sorry, let's call that rho for the integration. And the thickness is, what would that thickness be? What? Well, the variable that we're going to integrate over is rho, so this thickness is going to be an infinitesimal amount of rho, so it's going to be d rho. What? That's true. That's true. Okay, and then the increment of area is going to be equal to, so what's the area of that thing? This is a trick that comes up in these kinds of things a lot. Yeah, that's right. So think of straightening this thing out into a long rectangle. The thickness is d rho. The length is the circumference. So this is 2 pi rho. And so dA is equal to 2 pi rho d rho. And so now I sub p is the integral from 0 to r. So this variable r is the r of the entire shape. I sub p is 0 to r of, now we're using the definition, so it's going to be, this was our expression for dA, and the integrand has to be rho squared times dA. So this is rho squared times our expression for dA. And so that's the integral from 0 to r of 2 pi rho to the third d rho. So you get 2 pi rho to the fourth over 4, evaluated from 0 to r, and that gives you pi r to the fourth over 2. And so that's the formula we're going to use. I sub p for a circular solid cross-section is equal to pi r to the fourth over 2. And then you could use this same approach to calculate it for a hollow circular cross-section, and you'd get I sub p is equal to pi over 2 times the quantity r outer to the fourth minus r inner to the fourth. And that's for a hollow circular cross-section. Any questions about that? So, yeah. So the outer radius is our outer, inner radius is our inner. Okay. So I'll show how to do this calculation next time.